Welcome friends and families. Always keep yourself hydrated. Okay. Now today I'm gonna start with a little story. A few days ago, when me and my one of my friends was like after our class, we were going downstairs. Suddenly, my friend started telling me that Badhon, have you like we've all studied and heard about the electron spin in our high school classes. I was like, yes, we've heard about spins and we've done like spin quantum numbers and we've done something with this in our high schools. Yes. Then he told me that actually electrons don't have spin. I was like, what? Like then like, are you for real, dude? Then he told me that yeah, electrons have spins in their orbit, like they orbit the nucleus, but they don't orbit their own axis. Like I was like, you're kidding, right? Like all the time I've known that electrons have spins. They have plus of minus of spins, like these things. Like what are you telling me, dude? Then he started telling me that let me explain you now. Uh, at first, tell me what is spin. I was like, no, you tell me. Then he started explaining me like that. Suppose you have a disk, okay, a two-dimensional disk, and it's spinning, keeping this centered the main axis. It is like this. This is the main axis, and this disk is spinning. And what do you know by that? Like, suppose it's spinning clockwise. Okay. Now, what is spin in this? It's like if we consider two different points, okay, in this disk, then if you wanna explain spin in this, we can say that these 2 points are keeping a fixed distance with the center, and the points are making the same angle in a certain time t, theta 1 theta 2, and there is theta 1 equals to theta 2. Okay, I was like, okay, yeah, then every other points do the same. They keep the same distance and they rotate and make same angles in the center at a fixed time. Yes, that is spin. Now he asked me, like, is if you remember in atoms, what are the elementary particles? I was like, electrons, protons, neutrons, right? I was like, yeah. Then if we consider an electron, then it doesn't have any other points to consider. You can think electron as a disk because it doesn't have any other points to consider, and in a disk, in this situation, you can consider so many points, so many different points that have fixed distance with respect to the center, and also they make same angle at a fixed time in this circle or in this disk. But for electrons, you can't even make other different points because electron is itself is a point like particle. I was like, okay. Then he told me that's why in our traditional spinning, we like electrons don't have this traditional spinning. Why? Because electrons don't have these other points to consider. I was like, that doesn't make any sense. Like, it can spin, like if you if you think about a grain of salt, I can also rotate it, I can also spin it. So I can also spin the small and smaller objects. But he told me that electrons are different. Like it's way smaller. Like you can't break the electrons. So you can't think other points in the electrons that spins or that moves and keeps a certain distance with the center. I was like, okay. Then he concluded that that's why we can think of an electron that spins because electrons don't have spin. I was like, yes, okay. But if they don't spin, then why do we consider their spins in our studies? Like, why do we think them as they are spinning if they don't actually spin? He told me that well, though electrons don't spin, they have spin-like properties. I was like, what is spin-like property? He told me if something is spinning, it has some properties like angular momentum, moment of inertia. So like we can talk about the angular momentum in this. If some particle or if something is spinning with its velocity v, with a velocity v, and is its mass is m, then its momentum is p, and is spinning with respect to the axis and like the distances we can think about r, that we can say that the angular momentum we can say that l, angular momentum l vector is equals to r vector cross p vector. I said yeah, you can think like that. But for electrons, what? It told me though electrons don't spin, they also have angular momentum. I was like, are you kidding me, bro? You told me they don't spin. I didn't believe you. You proved me that actually it doesn't spin, but now you're telling me that it has angular momentum. How? Then he told me, like, I can explain you how it has angular momentum. I told him, then explain me. Then he started telling. For electrons, suppose it has angular momentum. Suppose if it has angular momentum, then electrons also have magnetic moment. They will also have magnetic moment, and if we place this electron in a magnetic field, then something will happen to the electron. If it has angular momentum, then it will have magnetic moment, and if it has magnetic moment, then if we put this in a magnetic field, the the electron will change his behavior. I was like, okay, if it has it has angular momentum, then maybe it it will do something. Like if it doesn't have any angular momentum, it doesn't have any magnetic moment, and if it has no magnetic moment, then even if we put a magnetic field in this system, the electron will won't do anything with the field. I was like, yes. That if it does something with the field, we can say that it has it has angular momentum. I was like, okay. Then he started telling me through experiments, if we put a magnetic field like this, and if we think about the electron and the magnetic moment is like in this direction, then the electron actually like how can we say wobbles around this particular angle, like it wobbles like this, it shakes like this. Okay, if it has magnetic moment in it. And how it can have magnetic moment? If it has angular momentum. Actually, through the experiments, we can observe that actually electrons do this ovaling motions, like it shakes, it kind of shakes. Like if you ever played Beyblade, if you ever played with a Beyblade, okay, then like uh, the suppose the Beyblade is spinning on this top. Okay, now if we somehow act, act a force on this Beyblade, a tiny force, our finger, like this, the Beyblade starts to oval around like this starts to shake, and after sometimes it drops due to the gravitational force. Okay, but here if we like instead of this force, if we act a magnetic field in it, it should also be of the same. If it has angular momentum like this Beyblade. Okay, now what? Now we can calculate the frequency at which the electron wobbles or shakes. I was like, how can I calculate the thing? He was like, I will show you now. Through a process called Larmor Precession. I was like, what is this? Then he started explaining me. Suppose there is an electron. Now electron can have two types of motions, like the orbital angular momentum, like suppose this is the nucleus and this is the electron, it orbits the nucleus, that's why it can have orbital angular momentum. We can write it as L. Also it has spinning angular momentum, and we are dealing with the spin angular momentum. And if we want to calculate the total angular momentum, we can also do that by adding these two vectors, spin angular momentum and orbital angular momentum. We are not going to that today, but we will discuss about this spin portion. Okay, like for this spin, how much the electron ovals in a magnetic field with B. Okay, okay, let us consider a electron. Okay, now if it has a angular momentum, we can write it as S, because this is the spin angular momentum because of the spinning, that's why you can write it as spin S. Okay, and because it has angular momentum, it will also have magnetic moment in the opposite direction of angular momentum, and we can write it as nu s. Okay, this is the magnetic moment and this is the angular momentum. Okay, now if we consider a like magnet like this. Okay, now the because of that, this is the south pole, this is the north pole. Now, because of this magnet, there will be a magnetic field working on this direction. Okay, right? Now, if we take the relation between the angular moment and the magnetic moment, we can write as G E by 2m, where G is some 2.00 something, 009 something, but we can write it as 2 and into, yes, this is the angular momentum and this is the magnetic moment, and this is the relation between them. Okay, right? And because of this magnetic field and this angular momentum, and this is the magnetic moment, because of this magnetic field and magnetic moment, there will be a torque working on this electron. And because for the magnetic moment and magnetic field, we know the torque is equals to magnetic moment cross multiplying with magnetic field. Okay, and what is the result of this cross multiplication? We can write this as us b sine theta. And what is the theta? Theta is the angle between them. Okay, right? Now, because of this torque, the torque, like, we can say that because of this cross multiplier, the torque is uh, perpendicular to the magnetic field. Okay, and also the torque is perpendicular to the magnetic moment. Okay, now because the torque is perpendicular to the magnetic moment, it will also be perpendicular with the angular moment. Okay, so we can also write that torque is perpendicular to the angular moment. Okay, now suppose this, the angle between the magnetic field and this angular moment is theta. Okay, and uh, like, this is the distance and this is s, and suppose for a small change in distance, for a small change in distance in angular moment, it will take time t or dt. For time dt, the change in this direction of angular moment or change in angular moment will be ds. Okay, suppose, and because this torque is perpendicular to the angular momentum, that's why we can say that this thing is 90 degree, and this thing is also 90 degree, this thing, and that's why we can draw a plane around that, and this plane is lying on, like, this field, they are parallel to each other. Okay, because it is also 90 degree, the other angle is also 90 degree. Okay, now if we consider it as s, then what is this? If we consider it as theta, and what is this then? This is nothing but s sin theta. Okay, from this triangle. Okay, now this s sin theta is the radius of this circle, and in this circle the angular moment, the direction of the angular moment will oval around this circle, and the electron will do like this type of motion, like this. Okay. Now to calculate the frequency at which the electron will wobble, like or will shake, we can calculate this by uh, we know for this like this if this the arc of the circle and this is the radius, then the angle cut in this we can say that d theta. We can say the angle is d theta. The angle d theta or d theta 1, we can say d theta equals to what? We can we can say that the angle cut theta 1 equals to what? Arc by what? This one, the radius. And what is the arc? This is the ds, the small difference in angular momentum. Okay. And the radius is what? S sin theta. Okay. And for this small change in angle, we can also say that the angular frequency is also d theta by dt. Okay. From this we or d theta 1. From this we can say that d theta 1 equals to omega dt. Okay. And replacing it in this, we can say that omega dt is equals to ds by s sin theta. And dt, taking dt in that, we can say that omega equals to ds by dt into 1 by s sin theta. Now what is this ds by dt? I didn't write that one, right? We can consider it like for this we can also say that the torque is also the change in angular momentum with respect to time. We can also count the torque like that. And replacing it with the torque, we can say that omega equals to torque into 1 by s sin theta. Now for the torque, we know like here the torque is nothing but the magnetic moment multiplied with the magnetic field s sin or and sin theta. And replacing it with, we can cut the sign and you can get omega equals to uh, nu s into b sin theta by s sin theta. Sin theta, okay. Then mu by s. From this we can say that mu by s equals to ge by 2m. Then we can replace this and we can get ge by 2m into b, and b is the magnetic field. And then so we can say that the frequency at which the electron will shake or wobble is dependent on the strength of the magnetic field. And this is purely we are taking that the electron has angular momentum. And actually by experiment we can prove this thing as true. So electrons actually have angular momentum, but they don't spin. They cannot spin with respect to their axis. They can spin like they can orbit the nucleus, and we can call it a spin. And also the spin will be L, like the angular momentum for the orbit we can consider it as L, and for the spin angular momentum we can consider it as S, and the total angular momentum we can write it as J. J vector is equals to L vector plus S vector. But this is a topic for another day. Okay. So my friend explained this thing to me, like I had so much more question to ask him, but I couldn't because by the time he finished explaining it to me, we are already downstairs. Then he told me that if you have any other questions, I'll let you I'll let you ask, or I'll explain to you another day. Okay, this is the thing, and the moral of the story is what, that though electrons don't have their, like, they don't spin with respect to their axis, but they have angular momentum that is corresponded to their axis, and because of that we we have to calculate and we have to consider it as spinning because of the angular momentum it has. Okay, so I think you guys understand, like, I could deliver it to you guys, and you've got to know a new thing, I think. So thanks for watching and stay hydrated. Thank you.